Back to the problem of the definition of average x acceleration and instantaneous x acceleration, or plain old acceleration. And it's the same as the relationship between average x velocity and instantaneous x velocity. We said that the average x acceleration is just the change in velocity divided by the change in time. And the instantaneous x acceleration that applies at a certain time, you just take that over a very tiny time interval. And graphically, that corresponds to the slope of the tangent line to the velocity versus time curve at a particular time is equal to the instantaneous x acceleration at that time. And that can be kind of confusing, even though we use the word acceleration in everyday life. Often we're easily fooled when we try to be precise in physics. So let's take some of these one by one. The first thing that disagrees with how we use the word in everyday life is that positive x acceleration, it kind of sounds like you're speeding up, but it might mean that you're slowing down, or it might not. So we have to tease that out of some examples, and we will. Similarly, negative x acceleration kind of sounds like you're slowing down, but it might mean that you're speeding up, or it might not. So here are some examples that flesh that out a little bit. If you are moving in the positive x direction, or the thing that you're describing is moving in the positive x direction, that means that the x velocity is positive. Okay? In that case, what does a positive x acceleration look like? What does the motion correspond to it? If you're moving in the positive x direction, positive x acceleration means exactly what you think it means. It means that you're going faster and faster in the positive x direction. And negative x acceleration kind of means what you'd think it would mean. You're moving in the positive x direction, but you're going more and more slowly as time goes on. And zero x acceleration just means you're moving with a constant velocity in the positive x direction. So those aren't too confusing. Where it gets confusing is where an object is moving in the negative x direction. Vx is less than 0. In that case, positive x acceleration means that you're actually slowing down as time goes on. You're moving to the left in the negative x direction, but you're slowing down. That's a positive x acceleration. Whereas a negative x acceleration actually means that you're speeding up in the negative x direction. And 0 just means, again, that you're moving at constant velocity in that direction. One way that I like to think about this, or explain it in words, is that you can think of the sign of the x acceleration as being the direction in which the x velocity is trending. So if I have a positive x acceleration, that means my x velocity is trending towards the positive direction. Now if I'm moving in the positive direction, that just means I trend more in that direction, so I speed up. But if I'm moving in the negative x direction, but my x velocity is trending towards the positive, I would have to slow down before I could start going the positive x direction. So a positive x acceleration means you're trending towards positive velocity. That means if you're moving in the negative x direction, you're slowing down as time goes on. Similarly, a negative x acceleration means you're trending towards a negative x velocity. Now, if you're already moving in the negative x direction, you trend more and more in that direction, you just go faster and faster. But if you're moving in the positive x direction and you have a negative x acceleration, that means you're trending towards negative x velocity. You've got to slow down and come to rest before you can go faster and faster in the negative direction. So it corresponds to slowing down up there. And 0 just corresponds to moving with constant velocity. So hopefully if you think of which way the velocity is trending, that helps. Two other words we need to be careful with because we use them in everyday language, but not always the same way we're going to use them in physics. Deceleration. When we say an object is decelerating, it means what it sounds like in everyday language, and that is that it's slowing down. Whenever it means it's coming closer and closer to being at rest. Now, acceleration sounds like it might be the opposite of deceleration, but it's not. Acceleration, the way we use that word in physics, just means that you're either speeding up or slowing down if you're moving in one dimension. It refers to both of those. So if you're slowing down, you're accelerating. If you're speeding up, you're accelerating in a different way. So it doesn't mean the opposite of deceleration. Acceleration just means the general phenomenon of a changing velocity. So that's something we're going to have to be careful with in language. Let's now move to a few voting questions to help tease out some of these ideas and think graphically in terms of position, velocity, and acceleration. If the velocity, so here's a car moving on the x-axis, the velocity of the car is non-zero at some time, could be positive or negative. Can the x-acceleration of the car be zero at that time? Yes, no, or depends on the velocity. If you need more time, pause the video. The answer is, this sounds really confusing when you read it or say it out loud, but it's actually quite simple when we think about it the right way. The answer is yes. Velocity of the car is non-zero. Can it ever have a zero acceleration? Well, yes, that's what constant velocity motion means. If I'm moving in the plus x direction at constant speed, that's zero acceleration. If I'm moving in the negative x direction with constant speed, that's zero acceleration. So both of those would be examples that would allow us to say yes there. This almost sounds the same, but it's just rephrased a different way, so it's a different question. If the x acceleration of a car moving on the x-axis is non-zero at some time, can the x velocity of the car be zero at that time? Yes, no, or depends on the acceleration. You really may need to pause this one because it's hard to sort of disentangle that sentence in your mind, so pause it if you need to. The answer here, again, is yes, it's possible. So it's up to us to think of some scenario where this is obviously true. And it's easier to start with a scenario where we think about it graphically. So I'm going to imagine position versus time graph and velocity versus time graph that correspond to this. An object is at some positive x, and at some positive x, and its x position is getting smaller and smaller, but it's also slowing down as time goes on, and it comes to rest at some point, and then it starts moving in the positive x direction. So it's heading towards negative x, slows down, comes to rest, and then starts moving in positive x direction. If I plot the corresponding velocity, x velocity versus time, slope of the tangent line was very negative, then a little negative, then zero, then a little positive, then very positive. So we go from very negative height of this graph to a very positive height of that graph. Notice, now let's read the sentence again. Can the velocity of the car be zero? Well, here's a point where the velocity is zero, right? The height of that velocity versus time graph is zero at that point right there. Is it possible that the acceleration could be non-zero at that time? Well, yes, the acceleration is non-zero because the acceleration is the slope of the tangent line of the velocity versus time graph. And the slope of the tangent line right at this point here is clearly positive. So that's a graphical situation. One way to think of that is kind of like another example that maybe is a little bit upside down is I throw a ball in the upwards direction. And for the purposes of this example, let's take plus y to be up. I throw a ball upwards, and I consider what it's doing right at the highest point of its motion. Okay? In that case, it's at rest right at its highest point. And at one point, it has a positive velocity on one side, and the other point, just before that, it has a negative velocity, or just after it. It's a little bit backwards compared to this one. But we have a situation, if I call plus y up, the graph would actually look like this for velocity versus time. First we had a positive velocity, then a zero velocity, then a negative velocity. At that point zero, is it possible that the acceleration is non-zero? Sure, it would have been negative. So throwing a ball up in the air would be an example of this at the point at which it's at its highest position. Third voting question, a rock is thrown straight upward and it soon comes back down. Take plus y axis to point upward from Earth. At the instant of time that it's at its highest point, what is the sign of the y acceleration? I may have given this away by the discussion I just did, but it's good to think about it again yourself. So plus y is up, points upward. And at that the instant of time at which the rock is at its highest point, what sign does its y acceleration have? Positive, negative, or zero? Again, pause if you need more time. The answer is negative here. I don't have a graph shown on this one, but it would be more like the velocity starts out positive, then it goes down to 0, and then it becomes negative. So the velocity versus time would look like this. At the time when it's at rest, that's when its velocity is at 0, the slope of the tangent line of that curve would be negative. So the answer for the acceleration is negative there. All right, let's think about one more graphical property, and then we'll take another break before moving on. We already know something about the relationship between position versus time and velocity versus time graphs, and that is if I want to know at time t equals 10 seconds what the x velocity is, I can look at the position versus time graph and attach a tangent line to it. And so I would say at 10 seconds it looks like the slope of the tangent line is positive. Sure enough, the height of this graph is positive there. Slope of the tangent line at 20 seconds would be negative. Sure enough, the height of the velocity graph is negative there. So in order to get from the position versus time graph to the velocity versus time graph, we look at the slope of the tangent line of the graph above. It should give you the height of the graph down below. Notice, slope of the tangent line is 0 there, height of this graph is 0. Where it's positive, the height of this graph is positive. Where the slope of the tangent line is negative, the height of this graph is negative. Same exact relationship that it goes between position and velocity versus time goes for between velocity and acceleration versus time. We use the same kind of analogous definitions. So, slope of the tangent line of the velocity versus time graph is negative here. The height of the acceleration graph is negative at that point. Slope of the tangent line is negative, height is negative. Slope of the tangent line is positive, height is positive, and so on. The question we're trying to get to on this graph is, how do I go in the reverse direction? We already know how to go from position to velocity and from velocity to acceleration. What if someone gives me the velocity versus time curve and we want to know something about the position versus time curve? How do we go upwards? And the answer is this, and you probably read about this in the reading. We're not going to dwell on it too much. The area underneath a curve down below tells you the change in the height of the curve up above. Okay, so the area under the velocity versus time curve between two times tells you the change in the height up above. So let's just take, this looks like maybe 3 seconds and 7 seconds, or maybe 4 seconds and 7 seconds. Between those two dashed lines, the area under the velocity versus time curve is some positive. We could calculate it by the area of this rectangle. We have to be a little bit careful because this has units of meters per second, and this has units of seconds along there. So there would be some units of meters associated with this area when we multiplied them together. But just think about the numbers. It's a positive area under here, and that means between t equals 4 and t equals 7, we expect to see a positive change in position or a positive displacement, and we do. Similarly, a negative area under the curve, and you have to know what mathematicians mean by negative areas. Anytime the curve is underneath the t-axis, we're going to consider those associated areas to be negative. So in this case, between t equals 23 and 27, it looks like the area under this curve is negative. We can get it by using the area of a triangle as 1/2 base times height. That means the change in position between this time and this time should be negative. And it sure is. It goes from a positive x value to a less positive x value between those two times. You can check all the points you want on here. Similarly, the same relationship goes for how you get from acceleration up to velocity. Areas under this curve down here correspond to changes in the value of this curve up here if you choose 2 times. So positive area here between 23 and 27, that means the change in the value of this graph should be positive. And it is. It's going up from a negative value to a 0 value, and that's a positive change. Area is negative between 10 and 15 under this curve, and between 10 and 15, the change in the x velocity is negative. It's going down from a positive value to a less positive value, and so on. So we now know, and we haven't practiced with it very much, but we will practice with this more, to go from position to velocity and acceleration versus time. Slope of the tangent line above gives the height of the curve below. Slope of the tangent line above gives the height of the curve below. And to go upwards, we think of the area between two times give us the change in the value of the one above between those two times. We'll practice a little bit with that one. But we won't use it nearly as much as the first set where we're going down here. And that's a reminder of me to end the video so we don't go too long in one session. So we'll be back in the next video with more on motion in one dimension.